Hello, this is Lovedeep Gondara, with Department of Computing Science, Fraser University. Today I'll present our work, Differentially Private Small Dataset Release using Random Projections. As we know, small datasets form a significant portion of releasable data, especially in high-sensitivity domains such as healthcare, where, in order to reduce unnecessary patient harm, most studies are designed with minimum sample size requirements. And in today's environment, it is also of increasing interest to share the datasets. In order to do so, in sensitive domains such as healthcare, we need to ensure that we protect the privacy of underlying users, that is, the patients in the dataset. Current methods that provide such privacy guarantees are based on the ad hoc method of removing identifiers such as the patient name, date of birth, postal code. But as prior published in literature, we know that such releases can be easily linked back to individuals. The methods providing provable privacy guarantees are based on differential privacy, where the current state of the art are based on synthetic data generation, where a generative model is trained with differential privacy on sensitive data, and it can then be used to sample from, where the samples are not only differentially private, but they follow the same distribution as the original data, leading to the same inference. But such methods seldom work in case of small datasets. The reason being the methods based on generative adversarial networks that are based on two contesting neural networks require larger datasets for training and to converge to the distribution of training data, which is simply not possible in case of small datasets. Other methods based on methods such as PAID fare even worse because they require partitioning the dataset into many disjoint partitions, which we cannot afford when we have such small datasets to start with. To overcome some of the challenges for differentially private release of small datasets, we propose DPRP, that is, the Differentially Private Data Release via Random Projections. This figure shows our method. We start with an input dataset X, from where we then proceed to taking its first random projection P across the columns, using our random matrix R. We then create the covariance matrix XC. We add noise M1 to the random projection to get its noisier version P prime. We also add noise M2 to the covariance matrix, and then we take its decomposition. Taking the noisy random projection along with the noisy right singular values, we get our reconstruction of X, that is X prime. From the extreme right-hand side, we can note that in reconstruction of X prime, only quantities that are involved are the noisy random projection P prime, the noisy right singular values B prime, and a random matrix R, which does not have any real data. In order to preserve privacy from X and to prove the differential privacy of X prime, we need to ensure the differential privacy of P prime, which is ensured by adding the noise matrix M1. And we ensure the differential privacy of the noisy right singular values V prime by adding noise M2 to the covariance matrix before decomposition, which makes the right singular values differentially private by the post-processing property. Then using the post-processing property, we can argue for the differential privacy of X prime as nothing else from the sensitive data, but P prime and V prime are used in the reconstruction. Further details can be found in the paper. For the empirical evaluation, we use 7 real-world datasets, and we show that our method outperforms the current GAN-based methods that are the conditional and unconditional GAN on all 7 datasets and for all privacy settings. Our method, being a reconstruction approach, is also extremely computationally cheap, and it offers one-shot reconstruction and is based on simple matrix manipulations. Being such a simple method, our method also does not involve any extensive hyperparameter tuning compared to deep generative models. Only tuning that is required for our method is the dimensionality of random projection P prime and the number of right singular values V prime used in the reconstruction, where using smaller number of right singular values would lead to a compressed reconstruction, and using larger dimensionality in P prime can improve utility, as the noise is inversely proportional to the number of to the dimensionality in our random projection. In the end, we would like to acknowledge the support from Ricardo for his valuable feedback, and would like to acknowledge the financial support from NSERC as a form of CGSD award and a discovery grant. Thank you very much.